Hello, this is Lab 1, analyzing the constant velocity of an object. The purpose for this lab was to test Newton's second law by using an object that's moving at a constant velocity. To do this, I rolled a soccer ball across a ping pong table from left to right, as seen in this video. Some main physics ideas. The central principle is Newton's second law, which states that a change in velocity over a change in time is proportional to the net force over mass, seen in the first equation. The second equation is used to find the position. It states that the final position is equal to the initial position plus the average velocity times the change in time. Now, our assumptions for this lab are that the net force is equal to 0. When plugged into the first equation, this allows Vf to equal Vi, and the average velocity to remain constant throughout. Now, an iteration of Newton's second law used in the computational model takes into account the net force being 0. In the second equation, it calculates the new position and adds onto it by changing the delta t slowly in each data point. In this experimental procedure, the ball was rolled in the positive x-axis direction and the interval of constant velocity was tracked using the tracker application. Some initial conditions for this lab: the soccer ball mass was 0.44 kilograms, the diameter was 0.22 meters, the initial position of the ball was 0.002 meters. The initial velocity, which we'll show how to calculate later, is equal to 1.33 meters per second, with the observation end time lasting about 0.834 seconds. Here's the ball rolling with the tracker device tracking the 26 data points of motion. As we can see, the ball is moving from left to right in the positive x-axis direction, with the y-axis being on the vertical. If we were to flip the axis, the speed would remain constant, but the direction would be in the negative x-axis direction instead of the positive x-axis direction. So we see on the graph on the right-hand side that a constant linear comparison between position and time. And we can calculate the initial velocity by taking the first two data points, finding the change between 2 and 1, and over the change in time between 0.033 and 0. So we used a computational model to test our predictions. We first edited the mass to 0.44 and the ball position and velocity to the numbers discussed earlier. We were then able to edit the calculation loop, which is where we're getting our data. We edited the while loop to while t is less than 0.834, the duration of our lab. The net force is equal to 0, and the new velocity and position equations are used using the first two equations of Newton's second law that we discussed previously, so that we could get a constant velocity. Here's the code for the motion, and here is the module running. As we can see when we look at that model, it's very similar to what we observed in the initial video of the ball rolling. We can see the graph on the left side. When comparing the model prediction and the experimental data, we see linear lines on both. However, the model data is slightly steeper than the experimental data, and this could be the result of a couple of potential errors. There's a noticeable difference that we saw. This could be due to initial velocity being miscalculated in the experimental model. In addition, the net force does not actually equal 0 in this situation, as forces of gravity, friction, and air resistance can keep velocity from being constant. And the soccer ball could have shifted while on the table, causing the experimental data to undershoot the model data as seen in the comparison. Thanks for watching.